Today, I'm going to be talking to you about hydrology, water resources, and environmental fluid mechanics, which is one of the areas of emphasis in civil engineering here at CU Boulder. So I'd like to start with an example that shows how the different pieces of water resources engineering can come together. The South Fork Dam was part of a large canal system in Pennsylvania that was designed to basically make rivers that were not navigable large enough, deep enough, wide enough, so the canals could pass. This was in an era where there weren't railroads that were able to, navigate this terrain, so the canals were used. As railroads got more capable, then the dams weren't needed anymore, and they were sold off. There wasn't necessarily as much environmental protection back then, so you could just go and buy a dam if you wanted to buy it. And a fishing club, the South Fork Hunting and Fishing Club, ended up buying this dam. And when they did so, they did not adequately maintain it. There were some safety features in the dam that were not seen as needed, and so they didn't use them. That was all well and good until you had this very bad rainfall event. One of the main things that you learn in water resources engineering is this idea of a statistical take on rainfall and other natural variables. And so we have this return period analysis that essentially shows you how rare it is for different kinds of events to occur. And you see rainfall of different durations, different depths, and then again, that return period in the colored lines. So on May 28th, 1889, a storm formed and dumped an estimated 6 to 10 inches in 24 hours. And you can see that if you go to the 24-hour line on the graph, you notice that that is quite a bit of rainfall. And what the recurrence interval or return period means is that on average, events that equal or exceed this magnitude only occur once every, say, 100 years, 200 years, 500 years, or so forth. So this was a historic rainfall event. And again, it is combined with a dam that was poorly maintained. And so when the dam started to fail, there was actually a guy who rode on horseback all the way to Johnstown to warn people. But one of the things that was kind of interesting from a sort of socio-political perspective is that the dam was kind of a mystery. It was a bunch of rich clientele. Nobody from Johnstown was even a member of this club. And so there were always these rumors about whether or not the dam was going to fail, such that when the dam started to fail, people didn't believe that it was actually happening. Luckily, nowadays, we have better technology to predict when floods are going to occur, as well as regulations on the safety of dams, which caused some to speculate that this may not have happened had those protections been in place. Reason why I wanted to bring this up is it shows how the water field is very interdisciplinary, even in its core. You think about the interface between structures, the engineers that build the dams and sort of what that looks like. Hydrology has to do with the water cycle. So how much rain are you going to see? How is that transformed into stream flow across the environment? And then what does that mean from an engineering perspective? How much is the public willing to pay? Are you willing to have your taxes increased, for example, to protect against these water events? And how do you educate the public about the importance of these things? As well as law. Two examples are, one, in the Western US, water rights are really important, and so different people own the water and have particular restrictions on what they can do with it. And also, in the Johnstown flood, there was no coordinated federal response to this. There weren't laws in place that essentially mobilized the federal government to help. Just to kind of drill down into a couple of different things that water resources engineers do, you can think about return periods from a statistical perspective, that it is describing how likely it is that a large event is going to occur at a particular time. But then we also use this as the design criterion to say, how much do we want to pay to build these structures, and sort of how much safety should they have, essentially. When we take a look at major structures, these are designed, if you go to the left, you see that they're designed for the highest return periods that we can calculate. And they're even designed on a different scale, which is this estimated limiting value scale, where 100% is the largest magnitude possible for an event that we can basically dream up what is physically possible, and we want to protect against that. But you can imagine that that level of protection could be very expensive in smaller pieces of infrastructure as well. So so-called intermediate structures are designed for a slightly lower return period, and then our poor cows are underneath this culvert, with minor structures being designed, say, for up to a 100-year return period or less. And it's interesting that society basically makes these decisions, and you learn about, in Europe, there may be different sort of preferences associated with protecting against floods versus in the United States and so forth. On the other side of the coin, we have drought that we're trying to protect against. This is not enough water, but it's interesting because there are a number of different definitions of how we can define what a drought actually means. And so you can take a look at the U.S. Drought Monitor, places in the United States that are currently in drought conditions. But when we think about it, one of the other big things that water resources engineers do is thinking about how to mitigate drought. You can build new water supply, but you need to be able to fill it. And plus, building new water supply, building new dams and reservoirs can be politically challenging. If you restrict usage, there's financial implications to that. So, for example, if a water utility is getting money from ratepayers, restricting usage can be a problem because it makes them lose money and they can't invest in equipment that they have. More efficient irrigation is an option, but it may not work, and it may have other implications associated with soil salinity and so forth. And so you can see in the diagram that we really look at water resources systems as a holistic system where the plants and the river and the human diversions all kind of come together, and we model these, and it allows us to think about how different interventions can actually affect the system. There's a lot of interesting courses available at CU. There's a list of them on the screen. You'll all do fluid mechanics as well as hydraulic engineering. And then there are some additional courses, including the engineering hydrology course that Professor Livna and I teach, as well as different offerings in groundwater. Now, what if I told you that many civil engineering jobs involve water? Even if you aren't in the water resources area, there's a lot of different things that water ends up touching on, especially related to things like construction, planning, and land development. But specifically in water resources, consulting firms are a big draw for our graduates. They're looking at different flood studies, water supply management, as well as working in the public sector. So the government funds a lot of different kinds of studies associated with water. And many of our students are at the Bureau of Reclamation, for example, and at other agencies, as well as doing graduate school, graduate research labs, and so forth. Thank you for your time.